Here we are talking about sampling distribution models. We're picking up where we left off last time. Last time we were talking specifically about assumptions and conditions, what's necessary to proceed with this idea of modeling a sampling distribution with a normal model. Well, last time it was all a specific type of data. We were talking about, is it heads or tails? When you're rolling a die, did you get a 1, 2, 3, or any other face of the die? Those were all categorical variables. When we're talking proportions, we're talking about specific classifications. Either you are classified as one thing or you're not. And with categorical variables, we found that the normal sampling distribution is really, really helpful. It allows us to kind of talk about how unusual our specific sample is. But quantitative data is different. There is no yes or no. We don't talk about proportions with quantitative data. I mean, sometimes we do. We might look at the average score on a test, and the scores might be proportions, but we're not looking at the proportions of those tests that received A's. That's different. Well, it just so happens that with quantitative data, we can follow almost the exact same procedure. The only problem is that in our quantitative data, when we were looking at our normal model, it was centered at a proportion, and our standard deviation involved a formula talking about the probability of success versus the probability of failure. Well, we don't have that with quantitative data, so there are a little bit of differences in here. The one thing that's consistent is whatever we expect our population to be centered at, and this time it's going to be a mean or a median or any other statistical measurement, that really is supposed to be the center of my sampling distribution. And what we can do is we're going to talk again about looking at simulations to try to figure out what's to be expected. Last time we did a computer program that was looking at average proportions. What happens if I were to talk about something different though? So if I'm thinking about rolling a die, I can talk about 10,000 tosses of a die, and I don't need to do this myself. I can run a simulation that'll calculate what are the results every single time. In doing so, maybe I get something like this. It's pretty expected. You have what we see here. We have a nice even distribution across the top here that is uniform. And uniform distribution basically just says the likelihood of any of my outcomes are all equal. That is just a single die. If I roll a die and I record the number on one of them, this is what I get. Now let's, instead of talking about one, we're going to start talking about multiple. And if I look at those dice, what would be the average of the number of dots on the faces? So here's my results after doing a simulation for 10,000 tosses. When I do 10,000 tosses, now because we're looking at multiple die, you should see here that we are centered more towards the middle, towards what we would expect the average to be. And you can think about it this way: the smallest number that we have on a die is 1, so the smallest average would be 1. The largest would be a 6, because 2 6s averaged together to give me 6, but there are a lot of combinations that'll average together to give me something in the 3 to 4 range, or actually 3 to 5. That's where a majority of my sums are going to be. This is not uniform anymore, but as it goes straight up and straight down, that is also not yet normal. Remember, we're looking at 2 dice. That is a small sample size. That's not enough to get my normal distribution, which should be more of a curve that'll allow me to use my 68, 95, 99.7 rule. So what happens when I pick up the number of dice? Let's go from 2 to 3. Already we see less of that kind of triangular peaked distribution that we had for 2. It's starting to look a little bit more normal. It's softening the edges here. And that's because now I have a greater range of sums. I don't have a limited number here. I'm starting to get more because I'm talking about thirds. If I still keep increasing my sample size, if I raise it to 5 die, well, now it's still possible to get an average sum of 1, but it's very unlikely. Same thing with an average sum of 6. Not really sums, an average number of dots of 6. we are still going to be more tightly clustered in the middle here. What you can see is even that spread is becoming less and less. So we're still seeing the greater the sample size, the more normal our curve. Now if I jump that up to 20 dice after running a simulation, and all of these are the exact same number of rolls, what you can see here, it still may be possible to get values as far out as that, but it's going to be very, very unlikely because a majority of my data is now really tightly clustered right in the center there. That's important to note because this is an extremely normal model with a much smaller standard deviation. The spread for most of this data goes that far. Spread for this data goes much less far. So this one went almost to, let's say, 5.75. This one goes from basically 3.5 to maybe, let's say, 4.6. And that's because if I take 1 plus 6, I get 7. Divided by 2 means an average of 3.5. So what we've seen here is that even when we're talking about means, average number of die on a dice when we roll it, we still have the same idea. The larger the sample size, the more normal the population. But in every instance, the average of my sample standard deviation, not my average of every single sample, but the average of of all of them together should be the population average. And it gets closer and closer to that 3.5. So we're still seeing this idea of a normal approximation that we had when we were talking about proportions. But how do I model this? How are things a little different, or are they the same? Well, we mentioned before a very important idea. It is so important that they call this the fundamental theorem of statistics. Now, almost every single math class has its own fundamental theorem. There's a fundamental theorem of calculus. There are fundamental theorems of algebra. Geometry has a wide range of fundamental theorems. Well, the fundamental theorem of statistics deals with that idea that the sampling distribution, not the population, but the sampling distribution, the collection of all the possible samples in the resulting statistic, becomes more normal as the sample size grows. Now that means any population. It doesn't have to start with a normal population. But you still have to have a couple of things. For example, you have to have independent observations. Things are starting to sound a little familiar here. When you have independent sample and you have some other things, the original population distribution doesn't matter. Uniform, we've seen, that already becomes normal. Bimodal will become normal. All of those will become normal. This is the fundamental theorem of calculus. Sometimes it's also called the central limit theorem. Those two are interchangeable. It is the heart of statistics. The idea that the larger a population sample gets, the more normal its sampling distribution will become. Now it is a little strange, okay? The histogram of the sample means. So we're not looking at the results from each sample. We're taking the mean of each sample. That's going to get closer and closer to the normal model. The histogram of the sample means. That doesn't mean that every mean that you take from every sample is going to be the same thing as the population. But if I map all the possible ones and take the average of all of those, it should be the same as the population average, no matter the population's shape. And of course, the shape does have a little bit to play. If your population starts off as a normal population, then our sampling distribution will get to that normal much, much quicker. But it's always going to work for larger samples. Larger is always better. So looking more at the central limit theorem, it says that the mean of a random sample is a random variable. This is what we've been talking about in class, where we say, okay, we're going to define it first as our random variable x, and we're going to put it in context. We're still doing that here. And then we're going to map the mean of all of those values. It can also be approximated by a normal model. Larger, the better. And the assumptions for means are pretty much the exact same thing as the assumption for proportion. For example, we start with the independence assumption. This guy is identical. the sampled values must be independent of each other. Now that'll be covered by randomness and something that says that we're not picking too many from my population to where one is going to affect the other. We still have the fact that the sample size has to be big enough. If it's not big enough, we're not going to be approximating the normal model. Now, how do we meet those? We really can't check the independence assumption with this one. It's not like flipping a coin or, okay, rolling a die. Those should be independent. But not every situation is. So what can we do? Well, believe it or not, exactly the same thing that we had before. You check the randomization condition. Was your sample conducted with some aspect of randomness? It doesn't have to be a simple random sample, but it does have to have randomness. And remember, if they don't say it, it didn't happen. The best you can do if they do not specify that the sample was taken randomly is you can hope that the sample was a representative sample. And that's the best we can do with that. But you have to write it down. You would say, we're not told that it is random, but we hope it is representative. You have to state that. If you don't state it, it doesn't happen. We also still have our 10% condition, and that is that our sample should not exceed 10% of the entire population size. That way we're not affecting the independence, the probability of one being chosen, probability of first guy being chosen versus the probability of the 10th guy being chosen. Those probabilities should still remain independent. Now, our large enough samples where things are going to change a little bit. The central limit theorem itself does not specify a specific cutoff for whatever size is large enough. We talked about in samples with proportions, NP and NQ had to be bigger than 10, but we don't have P's and Q's with means. So what do we have to do? Well, it really depends upon the context. What is the population itself? If the population starts off normal, we don't need as large of a sample. If the population is not, we're going to need a larger sample. So here's a whole bunch of craziness. The central limit theorem says that the sampling distribution of any mean or proportion is approximately normal. We've already discussed that. The proportions, we center it at the population proportion. The mean is P. For the means, it's the population. So the population mean. So here, the mean was where we believe the proportion to be. For this one, the mean is where we believe the sample mean to be. Now mu is mu. There's no surprise there. Standard deviations do have to change. The normal model for sampling distribution, this is a little bit different. Remember, Y bar is the mean of a sample. SD is the standard deviation of that sample. So how do we find the standard deviation of my sample? You take this guy, sigma, that is the standard deviation of the population. So that's the population standard deviation. And again, we have the square root of the sample size. So that's always there. Very similar to when we talked about the standard deviation of my proportion. Believe it or not, the standard deviation of the population is root PQ. Think about it this way. The population is all possible sample sizes of 1 that you can take. So if this guy is 1, that gives us what the original population is. So that's the same thing as distributing your square root inside. So we have the square roots for both of them, and we have the population standard deviations for both. Okay, so what's important out of all of this, other than all of this? What we're looking at here that's slightly different from what we did last time is now our normal model is centered at the mean, and our standard deviation for the normal model of my samples, we call that the standard deviation, is sigma, standard deviation of the population, divided by the square root of the sample size. All right, now let's kind of sum this up a little bit. Standard deviation of sampling distribution doesn't decline at a steady rate. It's not going to be, I add 1 to the sample size, my standard deviation goes down by a certain percent every single time. That's not true. Because in the denominator, we're dividing now by the square root of the sample size. So the variability still decreases as the sample size increases because you're dividing by a larger and larger number. But it's just not a constant rate. And at the same time, there's a certain point in time where we say, okay, the square root of 1,000 is not that different than the square root of 1,001, or even the square root of 1,500. So taking 500 more samples from these guys is not going to be a very big difference. The square root of this is going to be, I should have picked 100. It's going to be some number, I don't know, bigger than 10, less than 100. And this guy's going to be fairly close to that. I know there's some really, really complicated math. Between 10 and 100, I don't know where it is. But that's something called the law of diminishing returns. There's a certain point where just increasing your sample size really isn't going to do much for you, because you're just dividing by the square root of a slightly larger number. I mean, if you're looking at the square root of 4 is 2, square root of 9 is 3, so those we're seeing a little bit of a difference. But if we're looking at the square root of 100 is 10, even if we get up to the square root of 121, that's 11, so that's making even smaller and smaller differences as we go up. So variation is really the trick of all of this. We expect our distributions to be centered at the population mean or proportion. The standard deviation itself changes with the sample size, which is why it's so important to always indicate what your sample size is. Now, when we get together in class, we will go over again what the really, really important notations are necessary when we're talking about means. But you need to really understand the formulas for standard deviation of either a proportion, root PQ over N, and the standard deviation for a mean. And that is sigma, the standard deviation of the population, divided by the square root of N.